My name is Purnima, and I want to talk about NFS Ganesha and how we use it in our clustered NAS environment, or what we are proposing to do. So here's what my agenda is for today. I want to talk about what is NFS Ganesha at a very high level, what the NFS NAS requirements are, a little bit of architecture of NFS Ganesha, and then add on to what how we add clustering to NFS Ganesha and how we can use it in a clustered environment. And I will talk about what is Kamal and then the use cases of how we can use it. Are we proposing to use it? We can use it for things like the clustered duplicate reply cache or for recovery, which are one of the few things that we really need to handle in a clustered environment. So let me go ahead and start with what is NFS Ganesha. A lot of you probably already know it is an open source user level implementation of an NFS server, and it supports a number of different protocols. It supports v3, v4, 4.1, PNFS, and also 4.2. It can serve, that's the real beauty of it, it can serve multiple different file systems, and we will talk about how it can do that a little later. It can also manage huge metadata caches. And it has, because it can talk to different file systems, it has provision to access specific file system features. It can also act as a proxy server to serve remote NFS service, so it can act as an NFS client as well. And it is cluster manager agnostic. We want to keep it that way, even after we add the clustering support to it. It's an open source project with a small but growing community, and it's pretty active. This is the high-level architecture for NFS Ganesha, where it is the logging module. We have recently added LTTNG tracing support to it. There's the external control API, which DBus is used for that. And this is how the modular architecture for Ganesha is, which is a request comes in through the network 4 channel, the RPC dispatcher, and it can support a number of different protocols like v3, v4, PNFS. There is even support for 9P. Then requests a lookup in a cache inode, which is the cache for maintaining the metadata. And then it goes to this layer called the facade, which is file system abstraction layer. Now, this is the layer that sits on top of different file systems, and this is how NFS Ganesha can support multiple different file systems on the back end. So as long as you have your file system, maybe like VFS or XFS and GPFS, and you write a facade for it, it can be integrated into NFS Ganesha. So this is what I was talking about. The facade layer is an abstraction layer, and it provides an API to generically address the file system underneath. The cache inode layer is the metadata cache for the facade, and logging, logging can be to syslog or to files, and it also has support for LTTNG tracing. Now, facade up, if you just go back, facade up is the layer that is used to communicate from the backend facade into NFS Ganesha again. So we need support from Ganesha to the actual file system and the other way around, which is what this up layer is. Now that we have seen the really high-level architecture for Ganesha, I want to talk about some of the requirements that we have for enterprise NAS. And these are the main requirements where we want it to be reliable, redundant, and fail-safe. And mostly this is achieved through a clustered configuration. We want to serve structured and unstructured data over multiple protocols. It needs to be scalable in capacity and performance. That means it has to be flexible to scale up or scale out. And it has to be capable of supporting a large number of clients. Of course, we also need all these other enterprise features like tiering, dedupe, multi-tenancy, multi-protocol. It needs to be flexible to run on different platforms and serve a number of different kinds of data. And we have to support different security configurations and quality of service. Now, as we go along, I want to also come back to this slide maybe and talk about how NFS Ganesha can support a lot of these requirements that we have. So now to go back to Ganesha and some of the details of it, I want to focus on the file system abstraction layer, or the facade. The facade is the interface between Ganesha and the native namespace. So the backend file system, you could just write your own facade to any file system that you have and just integrate it with NFS Ganesha. And it is a dynamically loaded library. So you can load it into the Ganesha instance and just start accessing your file system from NFS. Now, it uses the file handler interface, and you can either use the VFS interface or it can directly call into the backend file systems interface. And you can combine multiple calls. One of the interesting features that you can use is integrate the Ganesha traces with the file system traces. So if you want to look at all your traces together, because a lot of times you want to see how they interact, the file system versus NFS, this is a really good way of doing it. And GPFS Facade supports these features. So you can actually integrate GPFS traces with NFS traces, look at all of this together. Now, Facade Up is the other way around. So this is the interface from the file system to the facade. And it is basically a thread for file system which calls into the backend file system and waits for events. Now, we really need this because if something gets updated outside of NFS, we need to know about it so we can invalidate the cache. Because NFS Ganesha has a big metadata cache, and if a Linux inode is updated, we have to notify and invalidate it. Also, there is a bunch of async activity which uses upcalls, which is grant or retry locks, recall delegations, and PNFS layouts. Right.
So one thread is it sufficient for your needs?
It is sufficient right now for file system.
Okay. So you don't have a performance bottleneck there.
Do that.
If it's just one thread, you don't have a performance bottleneck.
This is only for upcalls. So, for all the requests, it is hugely multi-threaded. But for upcalls, this is okay. And then, now I just want to go over what usually when we talk of NFS server, it's a single node NFS server. But most of the times that is not how it's used. When we use it in the enterprise, we use it as a clustered NFS server. So what is it when we use it as a single node NFS server? When we use it for V3, NFS V3, in general, the protocol is stateless for most of the file system operations, except when we talk of locking. In that case, we need the NLM and NSM, and there is state involved in that. Also, we have this grace period on server restart. So if we want to handle recovery and grace, we do need to go into this grace period. And these are things that, even though we call NFS v3 a stateless, there is state that we need to maintain. Now, NFS v4 incorporates the locking into it, and it is now a stateful protocol. And it has to monitor, basically it will look for release periods, and it will monitor the client. And these are, this is basically showing that this is the state that we need to maintain for V3 and for V4. Now when we go to a clustered NFS server, there are more things that we have to worry about. And they are in a cluster-wide, basically you have to do the cache invalidations and make sure it is propagated to all the nodes in the cluster. You want to coordinate the grace period across all the nodes in the cluster, because if one of your server reboots and if the grace period is not coordinated, you could actually grant a conflicting lock from another node. So Other things that you want to do is basically for high availability, where you want to store the state in the cluster to allow for failover and for lock recovery. Now I want to talk about what we are proposing to solve some of these issues and how we can make it easier to integrate into the clustered environment. We are proposing a cluster management abstraction layer, or the CMAL, and this CMAL would be very similar to what the FASAL is right now in NFS Ganesha. So each CMAL would have its back-end cluster manager support, which will also make it cluster manager agnostic. So this is what we will use for inter-node communication between the different cluster nodes. Now, we want to make it generic enough so that it can implement different clustering interactions for cluster DRC or recovery or DLM or any other clustering interactions that you want to provide. But doing all this, the main important thing here is that it still needs to be cluster manager agnostic. So the CMAL can have a backend CMAL which is specific to a cluster manager, and that is what will keep it, we can make sure it's talking to any. So here's how it will fit into the NFS Ganesha architecture. We have the CMAL, which is very similar to the FASAL, and this cluster manager abstraction layer will have a backend cluster manager abstraction layer, which will probably talk to different cluster managers like CTDB, GPFS, XIV, or even Pacemaker. And the cluster it will also have a similar up layer for interactions between having to send in messages from the cluster manager into Ganesha. Now, so this is how a cluster will look like. Suppose you have a 4-node cluster and you have node 1, 2, 3, 4 in the cluster. You have the FASAL, and the FASAL is talking to maybe a cluster file system at the back end. But what you want to look at is how the cluster manager, you also want to talk to the cluster manager, and that's where the CMAL will come in. So the CMAL will talk to the actual cluster manager that you have installed on the on your cluster. Now I want to go over some of the use cases and how we want to use this CMAL for some of these things. I will go over a couple of these, but it can be applied to other cases as well. So before I talk about cluster DRC, I want to talk about what is DRC, why do we need it? And we have operations which can be performed more than once, and they can be repeated any number of times without any issues, and those are called idempotent operations. But we have other kinds of operations called non-idempotent operations, and these are operations that we cannot repeat for a second time. Like, for example, a remove of a file. So, how do we handle this? And the NFS answer to this is we have an NFS reply cache or a duplicate reply cache. And the duplicate reply cache provides a way for the server to identify if there are any duplicate requests, and it will avoid processing those requests again and instead send the reply out from this cache. So what happens in a clustered environment? When we want to have the same DRC in the clustered environment, that's a lot of trouble because it is not cluster aware. Now you have your reply cache on each node, but if it is not cluster aware, then when a node fails over, the new node that takes over has no idea of the reply cache on the old node, and it is going to try to serve the request again. So the question is, should we live with this? Well, the answer is we are. We mostly are living with this issue. But I think that we should at least try to reduce it or alleviate it, if not completely eliminate. Completely eliminate, I think we cannot do that unless we store it persistently, but we can certainly reduce the problem. Now here is what we are doing with the Kamal to help with the cluster DRC case.